Welcome to The Explainer. Imagine waking up one morning, making your coffee, and realizing that every secure message, every single financial transaction, and literally every locked vault on the internet is just wide open. Sounds like a sci-fi movie, right? Well, it's actually a looming reality. You see, when commercial quantum computers finally arrive on the scene, they're going to have the sheer power to efficiently factor massive integers. What that means for us is that classical encryption methods, like the RSA system we literally use every day, will be cracked. Our current internet is going to become fundamentally unsafe.
So it really begs the question, what actually happens to our data when quantum computers crack the internet? Well, since our current data won't be safe anymore, scientists all over the globe are in an absolute race to build a fundamentally different kind of network structure. But, and this is key, they aren't trying to tear down the internet we already have. Instead, they're building a brand new architecture designed to coexist with our current setup. It's an architecture built specifically to harness the truly strange laws of physics to protect our information.
Okay, let's take a quick look at our roadmap for today's explainer. We're going to start with the quantum security threat, then we'll break down qubits and quantum entanglement. After that, we'll look at building quantum repeaters, move on to applications and unbreakable security, and finally, we'll wrap things up with a 15-year horizon. Let's get right into it.
Section 1. The quantum security threat.
Here's the core difference we need to understand. Our current classical internet relies on standard data transmission and encryption. And as we just mentioned, that's completely vulnerable to quantum algorithms. But the quantum internet, it actually transmits physical quantum states. That offers us something almost magical: unconditional security. Now remember, this quantum internet isn't here to replace the Wi-Fi you're using right now. It's going to run right alongside it in parallel, stepping in to provide an absolutely impenetrable layer of security exactly where we need it most.
Moving on to Section 2, Qubits and Quantum Entanglement.
To really grasp how this new network functions, we have to look at the data itself. You're probably familiar with classical bits. They're the little guys powering the laptop or phone you're using right now, and they convey information very simply, as either a 0 or a 1. But qubits, they are a whole different beast. They convey information through a combination of quantum states. They rely on incredibly tiny subatomic properties, like something called spin, which is basically the intrinsic angular momentum of an electron. So we're talking about information existing in these very unique, totally counterintuitive conditions that you only ever find at the subatomic scale.
And that brings us to quantum entanglement. This is a concept so wild that even Albert Einstein famously struggled to accept it. Entanglement is this highly peculiar correlation between quantum systems that is literally impossible in classical mechanics. Why is this so crucial? Well, entanglement allows us to connect different network nodes and transfer completely unknown quantum states faithfully, right across vast distances, at the speed of light. It's almost like a universal resource that you distribute across a network, inextricably linking two particles together, no matter how far apart they physically are.
But of course, there's a catch, and it's a massive physical hurdle known as the no-cloning theorem. This fundamental principle of quantum mechanics states that it is physically impossible to make a perfect copy of an unknown quantum system. So why does that matter for us? Well, think about our current internet. It relies heavily on repeaters. Those are devices that catch a signal, copy it, boost it, and send it on its way. Because of this no-cloning theorem, we can't just use standard repeaters for quantum data. If we try to copy a quantum state, boom, we instantly destroy it.
Which leads us to Section 3, Building Quantum Repeaters.
Since scientists literally cannot copy the data, they've had to invent a brilliantly complex workaround to send entanglements over long distances. It's a step-by-step process using intermediate quantum nodes. First, they generate short-distance entangled connections between nodes that are right next to each other. Second, they store that delicate entanglement in what are called quantum memories. Step 3 is where the real magic happens. They perform a Bell measurement, which is also known as entanglement swapping. Basically, they stitch those short connections together. And finally, step 4, they establish a direct entangled connection between the very first sender and the ultimate receiver, completely bypassing the physical space in between.
Let's break down how this memory-based quantum repeater approach actually looks. You can see how adjacent repeater nodes exchange photons to generate that entanglement. Once they pull that off, they store the fragile quantum state inside matter quantum memories. Then, using that Bell measurement we just talked about, they literally swap the entanglement down the line until the original sender and the final receiver share a direct quantum link. It is just an incredibly ingenious workaround to the whole no-cloning problem.
Now check out this alternative, the all-photonic approach. Notice what's missing here? There are absolutely no matter quantum memories. None.
This method relies completely on optical devices, things like single photon sources and linear optical elements. It operates kind of like a time-reverse version of that memory-based protocol we just looked at. By skipping the need to store data in physical matter memories, scientists are exploring a fundamentally different architectural path for the future network.
So we've got these two main approaches being tested in physics labs right now, and there are some real engineering trade-offs. The memory-based approach uses complex matter quantum memories, which means its overall speed is really held back by the actual communication distance. The all-photonic approach, on the other hand, skips all that and just uses optical devices. Its speed is determined entirely by the clock speed of those devices, which is pretty great because it lines up perfectly with the current all-optical trend in our everyday communications. Both are just absolutely massive feats of human engineering.
All right, Section 4, Applications in Unbreakable Security. So what is the most immediate real-world use for all of this? It's something called quantum key distribution, or QKD. QKD gives us communication that is theoretically perfectly secure. Because it relies entirely on the laws of quantum mechanics, it is fundamentally immune to eavesdropping. Think about it. Even if a spy manages to intercept the message, the simple act of observing that quantum state permanently alters it. The system immediately alerts the users that someone is listening in. And guys, this isn't just theory anymore. QKD is already up and running in prototype networks across Europe, Japan, and there's even a massive 2,000-kilometer network connecting Shanghai to Beijing right now.
But the quantum internet is going to go so far beyond just sending secure text messages. The applications are literally mind-bending. We're talking about secure cloud access where anyone can tap into a remote quantum supercomputer. It's going to enable completely unhackable financial deals and secure digital voting. It'll even let us synchronize atomic clocks across the globe with a level of accuracy we've never seen before. It's even going to revolutionize astronomy by letting us link telescope arrays across massive distances to give us an incredibly detailed look into the deep cosmos.
Finally, let's look at Section 5, the 15-year horizon.
Now, I want to be clear here, a fully operational global quantum internet is not something you can just log into today. Right now, this experimental network exists primarily inside physics laboratories and in regional testbed networks. So while connecting the entire planet is still uncertain and faces some really huge engineering hurdles, the incredible advances we've talked about today have absolutely proven the foundational science. We have working networks. Let's trace out a realistic timeline of what to expect. Today, we are firmly in the era of prototype networks and lab experiments. Looking into the near future, we're going to start seeing institutions and private companies getting cloud access to quantum computers. You probably aren't going to have a personal quantum computer sitting on your desk anytime soon, but you will access one through the cloud. And then, looking about 10 to 15 years out, the major goal is to have full, interstate quantum networks officially up and running.
To put a concrete number on that, researchers specifically estimate that interstate quantum networks will be established within the United States in that exact next 10 to 15-year window. That gives us a really solid, exciting time frame for when this highly secure parallel network is going to make the leap from small, regional tests into a massive, large-scale reality.
We have covered an absolute leap in technology today. We've gone from the basic zeros and ones of the classical bits we know, all the way to the totally mind-bending reality of quantum entanglement acting as an unbreakable bridge across the world. Which really just leaves us with one profound question to think about. How exactly will a completely unhackable parallel network reshape the future of human communication? When the trust of our data is actually guaranteed by the physical laws of the universe, the possibilities for our society are just absolutely limitless. Thanks so much for joining me.